Welcome. This video is going to look at the idea of metallic bonds, and this is found in your book in Chapter 7, Section 4. So metallic bonds occur because metals can only bond to themselves, not with another metal. They can bond to nonmetals and form ionic compounds like we've been talking about, but otherwise they bond with themselves. And this is because metals need to lose electrons, so sharing electrons with themselves like nonmetals can do doesn't really work, and transferring to themselves doesn't get them both stable. So instead, they form a lattice similar to an ionic compound where 8 to 12 metal atoms surround every single individual metal atom. So you have one metal atom surrounded by 8 or 12 other metal atoms. And it's crowded so their outer energy levels overlap, or their valence electrons. And the valence electrons end up getting pooled together, so each nuclei behaves stably. It behaves like it has 8 electrons. So here's a picture of kind of what it looks like, an ionic bond compared to a metallic bond. And you see with the metallic bond, these positive cations, that's the nuclei with the inner electrons lining up. And then the valence electrons, 1 or 2 typically, are just kind of free to move around it. So this is called a delocalized electron when it's free to move. Delocalized is a funny word meaning not local, and local means in the same area. So remember, with an ionic bond, we have a crystal lattice, but you've got cations and anions, your positive and negatives, alternating, which makes it rigid and hard with a high melting point and boiling point. It also makes it brittle when it's hit, and a poor conductor because those ions can't move easily. But with metallic bonds, you have a lattice, and just the positive nuclei line up, surrounded by the negative electrons. So they're also rigid and hard with fairly high melting points and boiling points. But now, instead of being brittle, when you hit them with a hammer, you can shape them into different things. And that's what we call malleable and ductile. It also means they're a good conductor both as a solid and a liquid because the electrons are free to move. And that's what we need, is a moving charge for good conductivity. Because the valence electrons surround these positive nuclei, they call it a sea of electrons. This is known as the electron sea model. And because they're free to move, again, they're called delocalized electrons. So the positive nuclei are also often referred to as metal cations. That's because it's not just the nucleus, but it's the nucleus and the inner electrons. So the freely moving electrons are considered to act like the anions. The positive nucleus with the inner electrons acts like the cation. So what are the metallic properties? They have high melting points, although it can really vary. Mercury is actually minus 38.9, so mercury is actually a liquid at room temperature, but it's the only metal that that's true for. Tungsten has a really high melting point at 3,422 degrees Celsius. So metals generally have a very high melting point. You'd have to have a lot of heat to melt something metallic, but it's not as high as ionic compounds. They also have high boiling points. As I said, they're malleable and ductile, so when you hit them with a hammer, you can shape them into different things. They're not fragile or brittle. They're also what we call durable. They don't wear down easily. And they're good conductors of both heat and electricity. And they also have luster, meaning they're shiny. They reflect light. So why do metals have these properties? All of these properties I just mentioned are because of the delocalized electrons. And the delocalized electrons mean that when you hit a metal with a hammer, you disrupt the pattern. As you can see in my picture to the right here, you can see the patterns being disrupted, but because they're all positive cations, it really doesn't matter if you shift them to the right, if you smash them down to one level. But with an ionic compound, when you do that, that disrupts the pattern because now it's not positive and negative. You have positive and positive and negative near each other, and it's going to split apart right there because of the repulsion between like charges. And so delocalized electrons give metals many of these properties. It also allows the electrons to move, to be conductive, to give it luster, etc. And the d orbitals of the transition metals make those transition metals even harder and stronger because they have even more mobile electrons available to them. The last thing to talk about with metals is this idea of metal alloys. A mixture of 2 or more elements that has metallic properties is called an alloy. Now remember, mixture means it's not chemically bonded, it's just physically mixed. And to do that, you usually have to heat the metals up so that they're liquids, allow them to mix evenly, and then you cool them back down. And we do this to get the good qualities of both elements. For example, if you want a metal that's lightweight but strong, You could take a very lightweight metal that's not necessarily very strong, like aluminum, and you could mix it with an element that's maybe a little heavier but stronger, and you end up with, you know, a fairly lightweight, fairly strong metal. So there's two kinds of alloys that typically form, and I'm just going to go through these quickly, just to make you aware of them than anything. So substitution and interstitial alloy. Substitution is just what it sounds like. One atom substitutes for another, and it occurs when atoms of the different elements are similar in size. So copper atoms can replace silver atoms to form sterling silver. Brass, pewter, 10-karat gold, those are probably all alloys you've heard of. So when you think you know about a metal and you can't find it on the periodic table, it's very likely an alloy and not a pure element. The other one is an interstitial alloy. And interstitial is a funny word, but interstices are like intersections. So it's when one atom is much bigger than the other atom, and the smaller atom can fill in the spaces or the interstices of the bigger atom. So it's kind of like pouring sand into a bucket of gravel. The sand will fill in the spaces between the gravel. So carbon is a common one added to iron to form carbon steel. And in this case, this is one of the few alloys where it's really just one metal with a non-metal, but it's still an alloy because it's still just a mixture. And carbon steel is often made because it's harder, stronger, and less ductile. So it's used in construction a lot. And here's a picture to give you an idea of the difference. A substitutional alloy, you can see that the red element has just been substituted in place of the black element. But with the interstitial, the much smaller red element is filling in the spaces between the larger black element. And that's metals in a nutshell.